Professor Ray here with another episode of Demystifying Physics, and today we're going to talk about temperature and heat. Two related but completely different concepts. And one of my viewers, who's a mechanical engineer that tutors engineering and science students, suggested I do this one because he saw a lot of confusion with his students on the difference between heat and temperature. So let's talk about that. First of all, we're going to say that heat is energy. And it's important to know that energy is the ability to do work. So we use heat every day for different things. It can be for a toaster, for a stove, for an oven, for a clothes dryer, for a heat pump, for the cooling system on a car, for the ovens at a brick furnace, for a nuclear power station, and the list goes on and on. We use heat to do work that benefits us. So it's very important for us to understand the differences in heat and energy. And while we're on the topic of energy, energy is measured in units of joules after the English physicist James Prescott Joule. And there's two kinds that we want to consider. The first is called potential energy, energy by virtue of position. I have this book, Elevated. It has energy by virtue of this position. We have kinetic energy, which is energy by virtue of motion. That was kinetic energy. If we add potential energy and kinetic energy together, we get what's called internal energy. And that's what we're concerned about with materials, because that's what's in the atoms and molecules that make up all materials, is internal energy. So let's talk a little bit about temperature. What is temperature? Temperature is just simply a measurement, and it's kind of an average energy of all the atoms and molecules in some material, but it doesn't matter what the material is or how much of it there is. It just matters that we're taking this average energy of whatever sample size we have. And in our calculations today, we're going to use temperature in units of Kelvin. And that's after Sir William Thomson, who was the first Baron Kelvin. That's who it's named after. It's also called the absolute temperature scale. So we'll work in units of Kelvin today when we speak about temperature. So temperature is this measurement of the average energy of some sample size of material. It doesn't matter what the material is or how much of it we have. Heat, however, that is a function of temperature. It's a function of the amount or mass of material, and it's a function of the actual material itself. And you'll see that come into play when we do these calculations that are coming up. So heat is energy. Temperature is a measure of average energy. It's not a function of mass or the material. So let's dig a little bit deeper. There is a mathematical equation that relates all this together. And that equation is Q equals MC and then delta T. Let's talk about this. So Q is the heat energy, and that's in joules. That's what we want to solve for. M is the mass of the material we have, and that's in kilograms typically. C is called the specific heat capacity, and the specific heat capacity has units of joules per kilogram Kelvin, or sometimes kilojoules per kilogram Kelvin, and that is unique to all the different materials that are out there. And then what is delta T? Delta T is the ending temperature of our material minus the starting temperature. So it's an after minus the before. We come up with this delta T. So we can see heat actually relies on this difference in temperature, but it takes into account the type of material and how much material. And this specific heat capacity is different for all kinds of materials. For example, the specific heat capacity of ammonia would be one value. For motor oil, it would be a different value. It would be different for Gatorade. It would be different for spaghetti sauce. It would be different for a piece of PVC pipe. Be different for a piece of cardboard in this cardboard tube. We have a steel railroad spike. It would be different for that. And I have a piece of copper. It would be different for that. So this specific heat capacity is different for every material. And that's used in the calculation of heat energy. And that's why it's going to be different than temperature. So let me move these out of the way, and we'll do a really quick experiment here to give you an idea. This experiment is actually to do a calculation on heat energy, and here's what we're going to do. So I'm going to take this pan right here, and I'm going to sit it on the table. Into this pan, I'm going to put some ice. So here's my ice. So the temperature of the ice is 32 degrees Fahrenheit. And if I convert that to Kelvin, that comes out to be 273.15 Kelvin. That's the temperature of the ice. The temperature in this room, ambient temperature, is about 70 degrees Fahrenheit. And if you calculate that, convert that to Kelvin, it's about 294.26 Kelvin. So those are the only temperatures we're going to work with in this set of problems. We're going to have this ice, the temperature of the ice, and the temperature of the room. So if I go through the calculations, I take Q, this is 0.45 kilograms of ice, and if I take the specific heat capacity of ice is 2.108 kilojoules per kilogram Kelvin. We'll use that in this equation. And we have the starting and ending temperature. The ending temperature is going to be 294.26, the starting temperature 273.15. So we put all those together, and when we calculate it out, we get the heat energy as this ice melts and comes up to room temperature is 20 kilojoules. 20 kilojoules. That's the heat energy, or the heat transferred, as this ice comes up, melts, comes up to a liquid, and then reaches room temperature. So if I add some more ice and I double it, so now we have 0.9 kilograms. So the specific heat capacity stays the same, and the starting and end temperatures stay the same. But now the heat energy we have, instead of being 20 kilojoules, is now 40 kilojoules for this amount of ice to melt and come up to room temperature. So we see the temperatures, the beginning and ending temperature, are the same, but because of the mass of the material, we have actually doubled the heat energy required. So let's take it one step further. What if we change the material? Instead of ice, I'll take this piece of iron right here. It's a little iron dumbbell, and I'll sit that right here, and that happens to be 0.45 kilograms, the same as our first measurement with the ice. Now here's the difference. The mass is the same, but the specific heat capacity for iron is 0.466. 0.466. But the starting and ending temperatures are still the same. They haven't changed. So when we look at the heat energy, or the energy that's transferred, as this little dumbbell comes from 32 degrees Fahrenheit up to room temperature, here it calculates out to be 4.4 kilojoules. 4.4, a lot less than what it did for the ice. The ice, remember, we started off, it was 20 kilojoules for our first batch. We doubled it and went up to 40. This is 4.4, and it's because of the heat capacity. So the temperature stayed the same, but the heat energy changed from all these. And it's important to note that higher level, the higher value for the specific heat capacity of ice, water is up even higher than that. And that's why in plants such as nuclear power plants, we use water and steam, because it's very, very good at creating the thermal energy to generate the turbines and to run the turbines and generate the electricity. So the numbers are very good for that. So basically, in a nutshell, that's the difference between temperature and heat. Remember, temperature is a measurement of the average energy of some sample size of some material. It doesn't care what the material is or how much it is. Heat, on the other hand, is a calculation. It's a function of temperature. It's a function of how much material and what the material is. And we can use that to calculate the heat energy that is transferred into or out of a system. So I hope that helps clarify the difference between heat and temperature. This is Professor Ray signing off.